So last time we saw that the first derivative told us where a function was going uphill to the right and where it was going downhill to the right. We saw that if f prime was positive on an interval, then the original function f was going uphill to the right. And we saw that if f prime was negative on an interval, then the original function f was going downhill to the right. And we use that to find the tops of hills, the bottoms of valleys, and so on. Today I want to take a look at the second derivative, and I want to specifically ask the question, what does the second derivative tell us about the shape of the original function? So what does the second derivative tell us about the shape of a function? Well, let's see if we can work that out for ourselves. Let's say we have the second derivative, and it happens to be positive on an interval, which I'll call I. An interval of x values, which I'll call I. Then the first derivative, since the second derivative is nothing more than the derivative of the first derivative must be going uphill there. It must be increasing. But that's not what I was asking about. I'm asking about the original function. If the first derivative is increasing, it means that the first derivative, the slope of the tangent line, is becoming less and less negative and more positive as I move from left to right. It's becoming less negative and or more positive as you move from left to right. If you started to draw that with your hands, where the slope is becoming less negative and more positive, what you end up with is a shape like this. And we call this concave up. It tells us how the original function is curving. It's curving upwards. It's shaped like a valley. If, on the other hand, the second derivative is negative on an interval, then what that means about the first derivative is that it's decreasing. And so, the original function, its tangent line is becoming less and less positive and or more negative. If you were to draw that as you move from left to right, what you end up with is something shaped like a hill. And so this is concave down. DN is my very favorite abbreviation because if you look at it upside down, it looks like up. So the first derivative tells you where a function is going uphill and where the function is going downhill. The second derivative tells us how the function is curving. Is it curving shaped like a valley, concave up with a cave in the top? Or is it curved shaped like a hill with a cave in the bottom, concave down? So I have one more definition to give you. If f has a tangent line at x equals c, and the concavity changes at x equals c from down to up or from up to down, we say f has a point of inflection at x equals c. So if you have a curve which is concave down and then it's concave up, then somewhere in the middle there is a point where it flips from being concave down to concave up. And here we have a point of inflection. If it goes from being concave up to concave down, that's supposed to be nice and smooth, then we have another point of inflection. Somewhere over here, there is a specific point where it goes from being concave up to concave down. Somewhere over here, there is a specific point where it goes from being concave down to concave up. Those are points of inflection.